Hello, everybody. And assuming the schedule hasn't changed, good morning. My name is Alexis R. Tudor, and I'm presenting to you virtually from near the University of Texas at Dallas. I regret that I wasn't able to make it to the conference, but I encourage you to write down any questions you may have, as I will provide my email at the end of this presentation for them. That being said, I am here to present on behalf of me and my other co-authors our work on using counterfactual justifications in goal-directed answer set programming to perform automatic knowledge gap detection and plan validation. Let's get started. First, an introduction to what it is we're actually doing. The domain in which this research resides is planning. As we are living through a golden age for AI and robotics, the embodied systems we are capable of creating have become incredibly advanced. I mean, look at this dancing dog. These complex systems require equally complex planning capabilities. Even simple robots for a single task, such as Roombas, require multiple levels of advanced planning. And with the embodiment of these planning systems into robotics, planning failures start to have real-world consequences. For example, even a fairly harmless embodied agent designed to put ketchup on omelets can have consequential failures, i.e., you now have ketchup everywhere. And that's pretty tame so far as use cases go. What about when your robot has a knife? Well, you would probably want your planning to be pretty precise, which brings us to the state of the art. For many planning applications, particularly embodied ones, the state of the art is various kinds of deep learning. And deep learning can do pretty good with planning. Particularly, a lot of research is floating around on how to do planning with LLMs. But these aren't perfect solutions. Ambiguity in the environment stretches beyond the bounds of the context of a deep learning system, and particularly, LLMs and deep learning systems perform poorly on circumstances they haven't encountered in training. Notably, when encountering a situation they don't know how to plan for, they can't recognize that. Instead, they can hallucinate, putting out confidently wrong answers. On the other end of the scale, there are planning languages designed with the traditional planning problem in mind, such as PDDL or strips. However, these systems are often confined to a single domain, and even within that domain, systems built for learning with planning languages require large amounts of data and are susceptible to noise in that data. Obviously, that's an oversimplification of the problem and solutions, but we'll leave it there for now. Logic-based systems, alternatively, can serve for broader problems and provide greater flexibility alongside generalizability from small quantities of data. These systems, unlike deep learning, are inherently explainable and justifiable, allowing much needed trust. However, most logic-based systems do not provide justifications when complete and correct plans cannot be found. That brings us to what we've done. This work specifically covers areas where a planner is not able to find a correct plan. We've created a counterfactual generation, or CG for short, module that can check if a plan is correct, or if a plan is incorrect, or a plan cannot be generated. It can identify where and why plans fail. We also provide an analysis of the use of this kind of reasoning for the detection of knowledge gaps in planning systems, as well as a validation that the CG module aligns with human evaluation of plans. Before we dive into those contributions, however, I'd like to take some time to provide background on SCASP and Vexer. Using SCASP as our symbolic reasoner is the key to this research, so I'd like to highlight some of the relevant advantages of it. Firstly, SCASP is a goal-directed answer set programming solver, which means that it doesn't need to be ground. That is to say that most answer set programs cannot be solved unless every unknown in the program can be quantified, which leaves some programs unsolvable. Unlike those grounding-based systems, SCASP only solves what's needed to answer a goal, creating partial answer sets and granting access to other logical tools like negation as failure, classical negation, and constraints. Secondly, SCASP is completely justifiable. What does that mean? Well, let's take a look at a quick demo. I have here a demonstration of SCASP, a very simple program that is used to tell if a bird can fly or not. So you see the definition of something that can fly is it's a bird that's not abnormal and can't explicitly not fly, where abnormal birds are penguins or those with wounded wings. Additionally, a penguin is a bird. So we have these examples. So let's say we want to tell if Tweety can flies. So let's draft our query as flies Tweety. And you can see that this holds, and it provides a justification of why. It holds because Tweety is a bird and there's no evidence that it can't fly or is abnormal. Now, what if we want to see if Sam can fly? So let's type in Sam. No. Okay. But why not? So here's one of the big features that's going to be useful in this research is you can put in not flies Sam and get a justification that Sam can't fly because while he is a bird, he is an abnormal bird and a penguin. So that's a very brief example, but these justification trees are important for understanding the research. Moving on, SCASP is fully justifiable and inherently explainable. It's a powerful non-monotonic reasoner that's also being used in a variety of other systems. There are downsides, which include intractability, difficulty with noisy data, and the need to represent knowledge in a symbolic format, which require a secondary harness to overcome. And speaking of that secondary harness, let's talk about the virtually embodied common sense reasoner, or VEXR for short. The primary contribution of this work, the CG module, is a standalone contribution that can be attached to any planning system, but it was first conceived as part of our research into improving VEXR. VEXR uses SCASP to combine simulated embodied environments with SCASP reasoning for planning. This is a high-level system diagram for VEXR, with each box representing a stage of the process. I'd like to quickly step over this diagram with you to contextualize our work with the CG module and present some of the relevant results that prompted the creation of the module. Firstly, the simulation environment that we use to represent a real-world environment to plan around embodiment. We use the virtual home simulation environment. Virtual Home has several useful features, including a physics engine for realistic interactions and an API that supports a mid-level control sequence. That is, you can use commands like walk to book, grab book, etc., instead of controlling the actual mechanics of an action. And finally, the creators of Virtual Home also created a database with 550 household tasks with human-created task breakdowns as a valuable resource for our learning systems. We convert the information from Virtual Home into SCASP through the Python harness. This encoding follows different pathways for immutable properties and dynamic properties. For example, this lamp will always be a lamp, and barring any unfortunate accidents, will always be a light source with a switch. Dynamic features are changeable, such as whether the lamp is currently on or what it's on top of. These properties are stored as a list so they can be reasoned over and changed. Next, those facts are added to our SCASP knowledge base as our awareness of the world around us. This information is combined with the knowledge of VEXR, learned from just 10 example tasks. Note that I say learned rather than trained in the traditional sense of machine learning training. We use the pre- and post-conditions of actions required to complete these 10 tasks as definitions in the knowledge base so that VEXR could reason over those actions and discover sequences of actions leading to a desired end state. Thus, we treat this as a traditional planning problem, where success is defined by the task end state, and so plans are guaranteed to be correct or not found at all. However, this method created intractable programs, as the context in even a small apartment was usually over 3,000 lines. That brings us back to VEXR, which provides several optimizations to decrease program execution time. I won't go into too much detail here, but just to alleviate concerns about tractability, I have some of the results from VEXR. These optimizations often bring plan creation down to a fraction of a second, which is even faster than an LLM most of the time. Finally, VEXR creates a plan for the stated task. From that high-level task, in this case read, VEXR identifies the actions to take and the specific actions to take, items to take those actions on to accomplish that task in the environment, which you can see here in our little demonstration video of the task. So to conclude this background section, VEXR is a planning system that guarantees plans that are correct and executable, with the downside being that if a correct and executable plan cannot be found, no plan or reason why is provided at all. This is, of course, better than confidently hallucinating a wrong plan, but still not ideal and may leave the user wanting. Vector is highly generalizable. From only 10 tasks to learn from, Vector was able to complete 71.6% of all 550 virtual home tasks, but only 71.6% tasks. Finally, Vector provides a good enough foundation of optimizations that we don't need to worry about execution time for the work in this paper. But let's go back to the question of completing more tasks. Do we introduce more training data to try and cover more of the tasks? How will we be able to guarantee completion of unseen tasks? How much more data would we require to learn the remaining 29%? Clearly, there are gaps in its knowledge base. How can we identify and correct those gaps in a way that maintains trust in the system? That leading question brings us to our contributions for this paper. The Counterfactual Generation module. Firstly, what is counterfactual reasoning? We define a counterfactual as the conditional statement that would need to be changed for an action plan to be changed from invalid to valid. This counterfactual can be used by a human reviewer or an AI system to understand why an action plan hasn't been carried out and how to successfully complete a task. We sought to employ reasoning using counterfactuals to help identify knowledge gaps in Vector's knowledge base, as well as to identify valid or invalid plans. As a brief visual demonstration of what a counterfactual is, I have an example here. Say you go to the bank and ask for a loan. You're denied. Your next question will likely be, why was I denied? What can I do to change that no to a yes? So if our theoretical bank loan applicant had these features, the counterfactual would likely be that the applicant's credit score is too low. And furthermore, if they increased it to 750, it would have been accepted. This counterfactual allows the applicant to understand the decision and turn it from an undesired decision to a desired decision. With that in mind, we wanted to bring the power of counterfactuals to Vector. When we can't find a correct plan, why not, and how can we fix it? The CG module is a SCAS-based add-on defined from the constraints directly provided by the virtual home simulation. Now let's dive into the details. The primary addition to Vector's main loop is illustrated here at the bottom of the diagram. If a task generates a successful plan, then the loop continues as usual. It's when a successful plan cannot be generated that the counterfactual generation module, or CG module, kicks in. The original Vector is guaranteed to be correct. Otherwise, it generates nothing. Therefore, our first step is turning on an unsafe version of Vector that will create invalid plans. To do that, we insert the possibility of non-legal actions into our plans. Ordinarily, no actions are added to a plan unless they are legal given the state of the world and the preconditions of the actions. However, through adding this line, we allow actions that will move us closer to the goal state, but are not legal, into the plan if an action that moves us towards the goal is legal and does not exist. Worth noting is that if this version is run on a task that did not produce a correct action plan, and it generates a plan that is terminable, this plan is guaranteed to both complete the task and be wrong. For example, a plan may involve grabbing something out of a closed container. In the plan generated by the unsafe Vector, the agent may simply grab the item without opening the container, completing the task in a way that does not account for environmental constraints. This partially incorrect plan becomes the input to the standalone CG module. The input to the CG module is always an ordered list of actions comprising a plan to complete a task, whereupon it pulls an initial world state. Then, for every action in the plan, it checks if the action is possible given that current world state. If so, the world state is updated with the consequences of that action and time progresses. If not, we then run the negation of if the action is possible and pull the justification like I demonstrated earlier. From there, that information could be used to augment Vector's knowledge base. Here's an example of a previously unperformable task that had a plan generated for it by the unsafe Vector. The task involves putting on shoes and a coat. The CG module identifies this task as having failed at step 8 because the coat is not reachable, a precondition of the walk action in virtual home, where reachability is defined by something not being inside of something that is closed. The coat is in a closed closet, and therefore, because none of the 10 tasks Vexer trained on involved opening something, Vexer could not create a plan for the task. Thus, we identify the need for the open action and can add that to our knowledge base. Although we made the CG module for knowledge gap detection for Vexer, our planning system, it can be used as a standalone module for any system that outputs an ordered list of actions comprising a plan. In particular, we believe this would be useful for LLM-based planners, either allowing them to self-correct after outputting an incorrect plan, or to be used in a training stage to directly feed results back into the LLM. For example, from our previous work generating GPT plans to compare with Vexer, this is GPT's least correct answer. GPT switches off the faucet and then rinses its mouth, which is illogical because you can't rinse your mouth with the water not running. Putting the plan through the CG module, we find that the plan is incorrect on step 15 because the faucet is already off. This agrees with human assessment of the plan, but provides additional explanation for why the plan is incorrect that is difficult and costly to get using something like Amazon Mechanical Turk to have humans evaluate plans. Okay, moving on. Let's briefly talk future directions and then get into some Q&A. Firstly, we performed a knowledge gap analysis on 13 randomly selected tasks that could not be accomplished by the base version of Vexer after having learned on only 10 tasks. Using counterfactuals, we were able to successfully identify the need for the open action, as none of the training tasks contained items needing to be opened. The need for the concept of outside also, as all of the training tasks took place inside of the apartment. The concept of other agents, and finally, the concept of drinking. For a few of the tasks, however, we weren't able to easily generate a counterfactual for them. A task like dance, for example, cannot be defined by its negation, but a little more on that later. In our analysis of the CG module's use on LLM-generated plans, we found that the results from the CG module match closely with the results from human analysis from our Vexer user study. The one task where the CG module disagreed with the human analysis was for the task called Feed Me, where the LLM took a tactic to describing in the first person the act of feeding you, the human. Though it was technically correct in that it violated no constraints, the leading theory is that the human participants found it to be kind of a weird way to go about describing a plan and translated that into marking it as incorrect. On top of comparing to the results from the Vexer user study, we ran a study on the 46 tasks provided by Huang et al. For their research into creating correct and executable plans with GPT. Without more details from their experiment, such as which plans specifically were labeled as correct or incorrect, it's impossible to say exactly how our results line up with theirs. However, the percent achievable from our analysis is in the same ballpark as theirs, which indicates the CG module does a similar job as humans yet again, to measuring whether a plan is correct and executable. Additionally, the CG module is faster than human analysis and could be used in automated validation rather than human-led, human-driven validation. This ability to know what one doesn't know and identify knowledge gaps is incredibly valuable when it comes to making a trustworthy system. By using counterfactual analysis of knowledge gaps, we can complete an additional 19.2% of previously unachievable tasks in Virtual Home, for a total of 90.8% completion with Vexer. This is again with only 10 tasks for learning alongside the counterfactual generation module, which provides us with a high level of generalizability. Again, this last 10 or so percent of tasks are things like dance or polish teapot. They're actions that aren't very easily defined by their negation for a counterfactual reasoning problem. and are just kind of one-offs. So this poses its own challenge in discovering how to solve these problems without just increasing the training to try and cover every one-off example. But still, 90.8% completion is pretty good, especially when you consider training off of only 10 tasks and using the counterfactual generation module. A lot of systems trained on only 10 tasks wouldn't even be able to solve those 10 tasks. So we're pretty pleased with the results. I'm going to take a quick drink over here. And lastly, let's discuss future directions. For Vexer, I'd like to see continued experimentation with logical techniques that could help us bridge the gap of the remaining 10 or so percent of tasks that are unachievable, without compromising the promise of learning from small amounts of data and the reliability, trustworthiness, and explainability of the system. Secondly, I would like to see if using the CG module could speed up or improve LLMs as planning systems through a automated fine-tuning for planning specifically. And the last thing I'll pose here is to investigate the human explainability of the justification trees and counterfactuals, which is a topic of much discussion in this area of plan repair and failed plans. In conclusion, the ability to autonomously detect knowledge gaps and validate the common sense correctness of generated plans is critical for creating trustworthy systems. The counterfactual generation module is a versatile contribution that can address this problem for a variety of task breakdown tools using the justifiability of SCASP. It's open source, and again, it could be used for any planning system that outputs a ordered list of actions that make up a plan. So pretty much all planning systems put out lists of actions. Thank you all for listening to my talk. And please, if you have any questions, feel free to email me at alexisrenee1@gmail.com. And depending on how good the setup is, you can also ask questions, I believe, of Dr. Gupta, who should be online right now, if you have any burning questions. Additionally, please feel free to scan the QR code on the left to take a look at Vexer, which includes our CG module. And again, thank you all and have a good rest of the conference. Bye.